There are nights when everything feels very quiet, and if you look up, you might notice the moon hanging there in the darkness. It's been doing that for longer than we can really comprehend. The same motion, night after night, century after century, for billions of years before any of us were here. We don't usually think about it. The moon just is. It rises, it sets, it changes shape as the month passes, and we accept this as part of the background of our lives. But there's something remarkable happening up there, something so steady and reliable that it's easy to overlook. The moon is moving. Right now, as you're listening to this, it's travelling through space at about 1,000 meters every second. That's faster than any aircraft, faster than sound. Yet when we look up, it appears perfectly still, peaceful, unchanging, and it never falls. You'd think after this much time, after 4.5 billion years of circling, something would have changed. You'd think gravity would have won by now. The Earth is pulling on the moon constantly, in every second, every moment, never resting. That pull is real, it's measurable, it's always there. And yet the moon doesn't get closer. It doesn't spiral inward. It doesn't crash. This is true for more than just our moon. Every planet in the solar system has been following the same path around the sun for longer than Earth has had oceans. Jupiter's moons, Saturn's rings, distant Neptune in the outer darkness, all of them moving, all of them held by gravity, none of them falling inward. If you've ever wondered about this, even briefly, you're not alone. It seems like it should happen. It feels like things that spin should eventually slow down, that orbits should decay, that what goes around should eventually come down. Our everyday experience tells us this. Spinning tops wobble and fall. Balls rolling in a bowl eventually settle at the bottom. Nothing keeps moving forever. Except, apparently, in space, things do. We're going to spend some time tonight exploring why. Not quickly, there's no rush. We're going to move through this slowly, the way you might walk through a quiet room at night, noticing small details, letting understanding arrive gradually without force. Because this isn't really a question about physics, not at first. It's a question about motion, and what happens when falling never quite finishes. It's a question about what feels true versus what is true, about why our instincts, which serve us so well here on Earth's surface, give us the wrong impression about what happens in the vast emptiness above us. The moon will still be there when we're finished. It will still be circling, and by the time we're done, that fact might feel less like something we simply accept and more like something quietly astonishing. You can stay as long as you like. We'll take this gently, one idea at a time, and see where it leads us. There's a reason the question exists at all. A reason. Why orbits feel like they should decay. Why it seems natural to imagine the moon slowly spiraling inward over time, eventually meeting some inevitable end. It's because almost everything in our experience does exactly that. If you've ever spun a coin on a table, you've watched it happen. At first, the coin spins upright, moving quickly, making that distinct rattling sound. Then gradually it begins to wobble. The wobble gets worse, the coin tilts further and further until finally it collapses flat against the table still. Or think about a bicycle wheel. If you spin it in the air, it will keep turning for a while, but only for a while. Even without anything visibly touching it, the wheel slows. The spinning gets slower and slower until eventually it stops. We've all seen this. We've all felt it. And somewhere in our minds, we've learned the pattern. Things that move eventually stop. Things that spin eventually settle. Energy runs down and motion fades. This isn't wrong exactly. Here on Earth's surface, it's completely true. It's so consistently true that it shapes our intuition about how the world works. When something keeps moving, we assume something must be pushing it. When something stops, that feels natural. That feels like the default. So when we think about the moon circling and circling, our instinct whispers that it should be slowing down. That after this much time, after all these billions of years, the motion should have degraded somehow. The orbit should be smaller than it used to be. Closer. Lower. Eventually, inevitably falling. It feels right. And if you've carried this question with you, wondering why the moon hasn't crashed, wondering what keeps it up there, you're responding to something real, a genuine pattern that exists everywhere around us. The problem is, the pattern doesn't apply. Not out there. What makes the coin stop spinning isn't some universal law that says spinning must end. It's something much more specific. It's friction. The coin rubs against the table. The air pushes against its surface just slightly. These tiny resistances accumulate. They steal energy bit by bit, and that's what makes the motion fade. The bicycle wheel slows for the same reason. Air resistance, friction in the bearing, tiny imperfections in the axle, each one pulling just a little bit of energy away from the spinning. You can't see it happening, but it is, constantly. And this is the heart of why our intuition misleads us. We live at the bottom of an ocean of air. We move through a world full of surfaces that touch other surfaces, where everything rubs against something else, where friction is so constant and so present that we barely notice it anymore. We've never experienced what it's like for something to move without anything touching it, without any air to push through, without any surface to drag against. We've never felt what motion is like when there's truly nothing there to slow it down. That's not a failure of imagination. It's just the truth of where we live. Our entire lives have been spent in a place where friction is everywhere, and so friction has become invisible to us. We don't think about it. We just expect things to stop. But space is different. Profoundly, fundamentally different in a way that's hard to internalize. And the moon, moving through that difference, never touches anything at all. We'll come back to that. For now, just notice the feeling, the instinct that says things should slow down. It's not foolish. It's just speaking from experience, an experience that doesn't reach beyond our atmosphere. Before we go any further, it might help to think about what we mean when we say something is falling, because the word carries a certain image with it, and that image might be part of what makes orbits feel confusing. When we think of falling, we usually picture something dropping straight down, a stone released from your hand, rain descending from clouds, an apple leaving a branch and moving directly toward the ground. Falling feels like it should be a straight line, a simple motion from higher to lower, ending when the object reaches the surface. And in that sense, the moon doesn't seem to be falling at all. It's not getting closer. It's not dropping. It's moving sideways, tracing a great circle around the Earth, and the distance between them stays roughly the same, month after month, year after year. So we might say the moon isn't falling, it's orbiting. Those seem like different things. But there's another way to think about this, one that's a bit gentler on our intuition. One that doesn't require us to imagine that gravity has somehow stopped working, or that the moon is immune to the pull that affects everything else. The moon is falling. It's just that it's also moving sideways, and it's moving sideways so quickly that the ground, the Earth, keeps curving away beneath it at exactly the same rate. Imagine you're standing on a perfectly flat, endless plane, and you throw a ball as hard as you can. The ball moves forward, but it also falls. Gravity pulls it downward the entire time it's in the air. It doesn't stop pulling just because the ball is moving horizontally. Both things happen at once. Forward motion, downward pull. The ball travels some distance before it hits the ground. If you could throw it harder, it would travel further before landing. The downward pull is the same either way, gravity hasn't changed, but the faster the ball moves forward, the more ground it covers before falling reaches the surface. Now imagine the Earth isn't flat. Imagine it curves. Because of course it does. And if you could somehow throw that ball fast enough, impossibly fast, faster than anything we can actually throw, something strange would happen. The ball would still be falling. Gravity would still be pulling it downward just as it always does. But the surface of the Earth would be curving away at the same rate the ball is falling toward it. The ball would fall and fall and fall, and it would never get any closer to the ground because the ground itself is curving downward just as quickly. That's an orbit. Not the absence of falling, but falling that never ends because there's no ground to reach. The moon is falling toward Earth constantly every moment, and Earth's surface is constantly curving away beneath it. The two motions balance perfectly. This doesn't require any special force keeping the moon up. It doesn't require energy or fuel or effort. It just requires that the moon is moving sideways fast enough that its fall matches Earth's curve. If the moon were moving slower, it would fall faster than the Earth curves and it would spiral inward. If it were moving faster, it would be trying to travel in a straighter line than Earth's gravity allows, and it would drift outward. But at the speed it's actually moving, about 1,000 meters per second as we mentioned earlier, the balance is exact. It's a kind of falling we never experience directly. We never get to feel what it's like to fall endlessly without approaching anything. Astronauts in orbit feel it. They describe it as weightlessness, though really they're in freefall the entire time, falling around Earth just like the moon does, just much closer. So when we ask why the moon doesn't spiral inward and crash, part of the answer is already here, hidden in what falling actually means. The moon is crashing in a sense, it's just crashing around the Earth rather than into it. Falling sideways, falling in a circle, and this has been true since the beginning. The moon didn't have to learn how to do this, didn't gradually find the right speed. It formed already moving, already falling, and the motion has simply continued, uninterrupted, for longer than we can easily imagine. We'll keep going. There's more to understand about why that motion doesn't fade, but perhaps now the question has shifted slightly. It's not, why doesn't the moon fall? It's, why doesn't the moon's falling ever change? It's worth pausing here to think about where the moon actually is, not just in the sense of distance, though it is far, about 384,000 kilometers away, but in the sense of what surrounds it. Nothing surrounds it. We use the word space so casually that it's easy to forget what it means. Space isn't just a place that's far away. It's not just the area between things, it's an emptiness so complete that it's difficult to truly comprehend from where we sit. Right now, you're surrounded by air. It's pressing against you from every direction with enough force to be measured, though you don't feel it because it's pressing equally from all sides. You're breathing it. You're moving through it. Every sound you hear is travelling through it. Air is so present, so constant, that it becomes invisible to our awareness. But it's there, and it affects everything. When you wave your hand, you're pushing air out of the way. When you walk, you're moving through air. When anything moves at all, here on Earth's surface, it's moving through this ocean of molecules, each one bumping into whatever is passing by, each collision transferring a tiny amount of energy, slowing things down bit by bit. This is what stops the spinning coin. This is what slows the bicycle wheel. Not some abstract principle, but actual physical contact, trillions and trillions of air molecules, each one contributing a minuscule amount of friction. The moon doesn't have this problem. Between the Earth and the moon there is no air. There are a few stray molecules here and there, remnants of Earth's atmosphere that have drifted up to extraordinary heights, bits of dust, the occasional atom of hydrogen floating through from somewhere else. But for all practical purposes, There is nothing there. Nothing to push through. Nothing to rub against. Nothing to transfer energy away from the moon's motion. If you could somehow take that bicycle wheel and place it in space, truly in space, away from everything, and give it a spin, it would keep spinning. Not for a long time, forever. Or at least for so long that the difference between a very long time and forever stops mattering. Billions of years. Longer than Earth has existed. The wheel would still be turning. This feels impossible to us because we've never experienced it. We've never touched something that doesn't eventually stop. But the reason things stop here isn't because motion naturally fades. It's because motion is constantly being stolen away by friction, by air resistance, by contact with other things. Remove those things and motion simply continues. The moon moves through this emptiness at tremendous speed, and nothing slows it down. There is no medium to push through, no atmosphere to create drag, just the vacuum of space, which isn't a thing at all. It's the absence of things. Gravity is still there, of course. Earth's gravity reaches out across that emptiness and pulls on the moon constantly. But gravity doesn't slow the moon down in the way friction does. It pulls the moon toward Earth, yes, but as we explored earlier, the moon is moving sideways fast enough that this pull just curves its path into a circle rather than bringing it closer. Gravity changes the direction of the moon's motion, but it doesn't remove the motion itself. And with nothing else there to steal energy from the moon's movement, the movement simply persists. This is the fundamental difference between here and there, between the world we know and the place where orbits happen. It's not that different rules apply in space, it's that space removes the conditions that make things stop. We live in a place where friction is everywhere, where resistance is constant, where motion always fades unless something actively maintains it. We've built our intuition on that experience. So when we think about the moon, we expect the same pattern. We expect something to be slowing it down even slightly, even gradually. But there's nothing there to do that. The emptiness protects the motion, the vacuum preserves it, and so the orbit continues, not because anything is keeping it going, but because nothing is there to stop it. It's a strange thought, isn't it? That motion could be more permanent than stillness. That in the absence of interference, things just keep moving. It contradicts everything we feel on a daily basis. And yet when you remove everything, all the air, all the surfaces, all the friction, this is what remains. Motion that doesn't need maintaining, paths that don't need correcting. The moon, falling sideways through nothing, century after century undisturbed. There's a principle here that might be worth sitting with for a moment, even though we won't dress it up in formal language or technical terms. If something is moving and nothing interferes with it, it just keeps moving. Not forever in the sense of some miraculous perpetual energy, but simply continuing the same direction, the same speed. Not because anything is pushing it along, but because there's no reason for it to stop. This is profoundly different from how we experience movement in our daily lives. Here, if you want something to keep moving, you have to keep pushing it. Roll a ball across the floor and it stops. Stop pedaling your bicycle and you slow down. Everything requires continuous effort to maintain motion. So we've learned to think of motion as something that needs fuel, needs energy, needs some kind of ongoing input. And rest, stillness, feels like the natural state. The place things return to when you stop trying. But that's only true because we're always moving through something. Air, mostly, or cross surfaces that create friction. Our experience is shaped by resistance. by things that oppose motion, and so motion feels temporary. In space, there is no resistance, and without resistance, motion doesn't require anything. It's not being maintained, it's just there, continuing the way it was. The moon isn't working to stay in orbit. It's not expending energy, it's not trying. It's simply moving, and that movement has never encountered anything significant enough to change it. This is why orbits can persist for billions of years without degrading. Not because they're being sustained by some hidden mechanism, but because there's nothing there to make them fade. The motion was there at the beginning, when the moon formed, when it first found itself moving sideways at just the right speed, and it's still there now, unchanged, undiminished. It's a kind of permanence we don't have access to in our everyday world. Here everything winds down, everything stops. But out there in the silence and emptiness, some things just continue. The moon is one of them. So we have two things happening at once, and it's worth holding them both in mind together for a moment, because their relationship is what creates an orbit. There's the moon's motion, that sideways movement, that tremendous speed carrying it along a path that would, if nothing interfered, take it in a straight line out into space away from Earth entirely. And there's Earth's gravity, pulling inward constantly toward Earth's centre, trying to bring the moon closer. These aren't fighting each other exactly. They're not in conflict. They're just both happening, both real, both present every moment. And together they create something neither one would create alone. The sideways motion wants to carry the moon away in a straight line. Gravity curves that line inward. The result is a path that circles, a compromise between going straight and falling inward, a trajectory that does both and neither. If the moon were moving slower, gravity would win more decisively. The inward pull would curve the path more sharply, bringing the moon closer with each orbit, creating a spiral that eventually ends at Earth's surface. If the moon were moving faster, it would resist the curving more. Gravity would still pull, but the moon would be trying so hard to go straight that the curve wouldn't be enough. It would drift outward, eventually escaping Earth's hold entirely. But at the speed the moon actually moves, the balance is exact. The curve inward matches the motion sideways perfectly. The path closes into a circle, or close enough to a circle, that the difference doesn't matter for what we're thinking about now. This balance doesn't require adjustment. It doesn't need fine-tuning. Once it exists, once the speed and the distance and the pull all align, it simply continues. The moon doesn't need to check its speed or correct its course. The motion persists, the gravity persists, and the circle persists. And this is true not just for our moon, but for everything in orbit anywhere. Every planet around the sun, every moon around every planet, every artificial satellite we've ever launched. They're all balancing these same two things, the desire to move straight and the pull that curves that straightness into a circle. It's not a fragile balance either. Orbits are surprisingly stable. You can disturb them a little, give the moon a slight push, or pull it slightly closer, and the orbit adjusts, reshapes itself, finds a new balance. It doesn't collapse, it doesn't require perfection. What makes an orbit decay isn't an imbalance between motion and gravity. Both of those can coexist indefinitely. What makes an orbit decay is the introduction of a third thing, something that steals energy from the motion itself, something like friction, something like drag. And in the emptiness between Earth and Moon, there is no third thing, just the motion, just the pull, just the path they create together. It's been this way for a very long time, and without anything there to interfere, it will continue for a very long time more. There's another piece of this that might need addressing because it's easy to imagine that even if nothing slows the moon down, Earth's gravity might still be slowly reeling it in, like someone pulling on a rope, drawing something closer bit by bit. After all, gravity is always pulling. It never stops. It never weakens with time. Right now, at this very moment, Earth is pulling on the moon with exactly the same force it pulled with 1 billion years ago. The same strength, the same direction, always inward. So why doesn't that pull eventually win? Why doesn't the moon get closer? The answer has to do with what gravity actually does and what it doesn't do. Gravity pulls. That's true, but pulling doesn't automatically mean bringing closer. What gravity does is change motion. It changes the direction something is moving, or it changes how fast something is moving, or both. But it doesn't simply drag things inward on its own. Think about that ball we imagined earlier, the one thrown across a flat plane. Gravity pulls on it the entire time it's in the air, but the ball doesn't just drop straight down from where it leaves your hand. It follows a curved path, forward and downward at the same time. Gravity is pulling downward constantly, but the ball still travels horizontally before it lands. The pull is constant, but what that pull does depends on how the object is already moving. For the moon moving sideways at tremendous speed, gravity's pull doesn't bring it closer. Instead, it curves the sideways motion into a circle. The pull is always there, always pointing toward Earth's center. But the moon's speed means that pull becomes a change in direction rather than a change in distance. This is different from something being slowly pulled in. If you're holding a rope attached to something and you pull steadily, yes, you'll bring it closer. But that's because the rope is removing energy from whatever motion the object had. The rope creates tension, friction, resistance. It's not just pulling, it's also slowing the object down, stealing its sideways motion. Gravity doesn't work that way. Gravity doesn't steal energy from the moon's motion. It redirects that motion, curves it, bends it into a circle, but the speed stays the same. The energy stays the same. And as long as those stay the same, the distance stays the same. Earth pulls on the moon with the same force it always has. The moon responds to that pull the same way it always has, by curving its path. And that curved path remains a circle, not a spiral, because nothing is removing the energy that keeps the moon moving at its current speed. The pull is real. The pull is constant. But constant pulling, when nothing removes energy from the motion, doesn't mean getting closer. It just means continuing to orbit. This has been true since the beginning, and it remains true now. The moon circles, the Earth pulls, and the distance between them stays roughly the same year after year, eon after eon. So if the moon's orbit is stable, if it can continue indefinitely, without spiraling inward, it's worth asking, what would it take to actually make an orbit decay? What conditions would need to exist for the spiraling we instinctively expect to actually happen? The answer is simpler than it might seem. You'd need something to steal energy from the motion, something to slow the object down bit by bit, until the balance between sideways speed and inward pull tips in favour of the pull. The most obvious thing that can do this is atmosphere. Air. The same friction we talked about earlier that slows spinning coins and bicycle wheels. If the moon were orbiting closer to Earth, much closer, it would eventually encounter the outer edges of our atmosphere. Very thin air, just a few scattered molecules, but still something. And each molecule the moon passed through would steal a tiny amount of energy. Not much from any single collision, but over time, over millions of encounters, that energy loss would add up. The moon would slow down just slightly, and as it slowed it would no longer be moving fast enough to maintain its circular path, Gravity would pull it a bit closer. Now orbiting at a lower altitude, it would encounter slightly thicker atmosphere, more drag, more energy loss. It would slow more, fall closer, encounter even thicker air. This is what happens to satellites in low Earth orbit. They're moving through the very upper reaches of the atmosphere, where the air is extraordinarily thin, but it's there. And over time, months, years, sometimes decades depending on the altitude, that thin air steals enough energy that the orbit decays, the satellite spirals inward, encounters thicker atmosphere, heats up from friction, and eventually burns up or crashes. But the moon is far beyond this. The wisps of atmosphere that might reach a few hundred kilometers above Earth's surface are nothing compared to the 384,000 kilometers between us and the moon. There is no atmospheric drag, no friction from air, nothing stealing energy that way. There are other, more subtle things that can change orbits over immense timescales. Tidal forces, the way the moon's gravity pulls on Earth's oceans and Earth's gravity pulls on the moon itself, can transfer energy between the Earth's rotation and the moon's orbit. But interestingly, this actually pushes the moon farther away, not closer. The moon is very slowly drifting outward, gaining altitude at a rate of a few centimeters per year. Collisions with other objects, asteroids, comets, debris, could change the moon's orbit dramatically. But these events are rare, and they're random. They're not a gradual decay, they're sudden disruptions to an otherwise stable system. What we don't have is the constant everyday friction that makes things stop here on Earth's surface. And without that friction, without something continuously stealing energy, the orbit simply doesn't decay. The conditions that would cause spiraling inward are specific, and they're absent. So the moon continues undisturbed, tracing the same path it has traced for longer than we've been here to notice. We should probably acknowledge something here, something that makes all of this even stranger when you really sit with it. Some orbits do change, very slowly, over timescales so long that they're difficult to hold in your mind in any meaningful way. We mentioned a moment ago that the moon is actually drifting away from Earth, not toward it. Moving outward at about 3.8 centimeters per year. That's roughly the rate your fingernails grow. Barely noticeable, but it's real, and it's measurable, and it's been happening for a very long time. Over the span of a human lifetime, the moon moves away by about 3 meters, the distance from one end of a small room to the other, completely imperceptible. You could watch the moon every night for your entire life and never notice any difference in its size, its brightness, or how long it takes to cross the sky. But over 1 billion years, that 3 centimeters per year adds up to 38,000 kilometers, a distance greater than Earth's circumference. Enough to change things noticeably if there were anyone around to compare. And this has been happening since the moon formed. Billions of years ago, the moon was much closer than it is now. Close enough that it would have appeared enormous in the sky. Close enough that tides would have been dramatically more powerful. The Earth was spinning faster then, and the moon was orbiting faster, and very gradually, over unimaginable stretches of time, energy has been transferring between Earth's rotation and the moon's orbit. The Earth's day is getting longer, microseconds at a time. The moon is drifting farther away, centimeters at a time. Both changes so slow that they might as well be invisible, but continuous nonetheless. This isn't decay though. It's not spiraling inward. It's the opposite, a slow expansion, a gradual widening of the orbit. But it illustrates something important about the timescales we're talking about when we discuss orbital mechanics. Things can change in space, but they change so slowly that stable and unchanging become meaningful descriptions, even when technically, microscopically, things are shifting. 1,000,000 years is nothing in these terms. 1,000,000 years from now, the moon will have drifted outward by 38 kilometers. You could measure it with precise enough instruments, but you couldn't see it. The orbit would look identical. The month would feel the same length. Everything would appear exactly as it does now, 10 million years, 100 million years. These are the scales where changes start to become noticeable, where orbits can shift enough that the differences matter. But even then, we're talking about gradual adjustments, not catastrophic decay. The orbits of planets around the Sun are even more stable. Jupiter has been following essentially the same path for over 4 billion years. The solar system has settled into a configuration that persists across timescales we simply cannot experience or truly comprehend. Yes, things change. Over deep time, planets can shift slightly, resonances can develop, orbits can become more elliptical or more circular. But these are slow drifts, not spiraling decays. And they happen over periods so extended that entire species arise and go extinct in the time it takes for an orbit to change noticeably. This is part of why the question, why don't orbits decay, has such a clean answer. Because on human timescales, on the timescales we can actually perceive and care about, they don't. The moon was circling Earth when the first animals crawled onto land. It was circling when the dinosaurs lived and died. It was circling when the first humans looked up and wondered about it. And it will still be circling, barely changed long after we're gone. The persistence isn't absolute or eternal in some mystical sense, but it's close enough that for all practical purposes, for anything we might want to understand about our world and our place in Nesca, orbits are permanent. They don't need to be maintained. They don't degrade on any timeline that matters to us. They just continue quiet and reliable, marking time on a scale we can barely conceive. It's worth pausing here to talk about artificial satellites because they do behave differently. And that difference might seem to contradict what we've been saying about orbits being stable and long-lasting. If you follow space news at all, you've probably heard about satellites decaying, about objects falling back to Earth, about things burning up in the atmosphere after years or decades in orbit, old rocket stages, defunct satellites, pieces of space debris, all of them gradually losing altitude, spiraling inward, eventually meeting their end. This happens. It's real. And it might make you wonder whether orbits are really as stable as we've been describing. The answer has to do with where these satellites are orbiting. Most artificial satellites, especially those in what's called low Earth orbit, are much, much closer to Earth than the Moon is. The International Space Station, for example, orbits at an altitude of about 400 kilometers. Communication satellites, Earth observation satellites, many of the objects we've put into space, they orbit within a few hundred to a few thousand kilometers of Earth's surface. And at those altitudes, there's still atmosphere. Not much, not anything you could breathe or even notice if you were there, but enough. The edge of Earth's atmosphere doesn't end cleanly at some specific altitude. It fades gradually, becoming thinner and thinner, but traces of it extend surprisingly high. At 400 kilometers up, where the space station orbits, there are still a few stray molecules of oxygen and nitrogen drifting around, left over from the thicker atmosphere below. Not enough to create any noticeable drag in the way we'd experience it, but enough that, over time, over weeks and months, they steal tiny amounts of energy from the satellite's motion. This is exactly the mechanism we talked about earlier. Friction, dragging something, stealing energy from the orbit. When energy is removed, the orbit decays. The satellite slows slightly, drops to a lower altitude, encounters slightly thicker atmosphere, slows more. The spiral begins. The International Space Station deals with this constantly. Every so often it fires its engines to boost itself back up to a higher orbit, replacing the energy lost to atmospheric drag. Without these periodic boosts, it would gradually spiral inward over a period of months or years and eventually burn up in the atmosphere. Old satellites that can no longer fire their engines do exactly that. They drift lower, encounter more drag, and eventually re-enter. This is why low Earth orbit has to be managed carefully, why there are concerns about space debris, why objects don't just stay up there forever once launched. But notice what's different here. It's not that orbits naturally decay, it's that these particular orbits exist in a place where friction still exists, where there's still something there to steal energy. The Moon, orbiting at 384,000 kilometers, is far beyond this. The wisps of atmosphere that affect satellites at 400 kilometers are entirely gone by the time you reach even a few thousand kilometers up. By the time you're at the Moon's distance, there's nothing. Just vacuum, true emptiness. And in that emptiness, the Moon's orbit is stable in a way that low Earth orbit simply isn't. There's no atmospheric drag, no friction, no slow bleeding away of energy. The orbit continues unchanged, not because the Moon is somehow special, but because it's far enough away that space is truly empty. So when we say orbits don't decay, we mean orbits in deep space, away from atmospheric interference. The Moon, the planets, the moons of other planets, these are in true vacuum, and their orbits persist across billions of years. Satellites in low orbit are in a transitional zone, still just barely touching the edges of Earth's atmosphere, and that makes all the difference. They're not in deep space yet. They're still close enough that Earth's atmosphere, however thin, reaches them. The difference isn't about the physics of orbits, it's about the environment. Remove the atmosphere entirely, and even satellites would orbit indefinitely, just like the Moon does. That's the distinction. And it's why we can say with confidence that the Moon isn't going anywhere. It's too far away for atmosphere to reach, too far away for friction to exist, orbiting in true emptiness, where motion simply continues. There's something quietly extraordinary about looking up at the Moon and knowing that it's been tracing that same path for longer than almost anything else you can point to. The Moon has been orbiting Earth for approximately 4.5 billion years. That's not a metaphor, or an approximation meant to evoke vastness. It's an actual span of time that can be measured, studied, understood through geology and physics and the patient work of scientists examining rock samples and running calculations. 4.5 billion years. Before Earth had oceans, before the first single-celled organisms appeared, before continents formed and shifted and reformed. The Moon was already there, already circling, already following the same fundamental motion it follows tonight. Every planet in our solar system has been orbiting the Sun for roughly the same amount of time. Jupiter, distant and massive, moving through its 12-year cycle. Saturn with its rings. Mars, Venus, Mercury, all of them settling into their paths when the solar system was still young, still forming, still cooling from the cloud of gas and dust that collapsed to create it. And they're still there, still following those paths, not because anything maintains them, but because nothing has stopped them. The moons of Jupiter, Europa, Ganymede, Callisto, Io have been circling Jupiter for billions of years. Saturn's moon Titan has been orbiting through the cold outer reaches of the solar system since before Earth's surface was solid. These aren't recent arrangements. They're ancient patterns, formed early and persisting ever since. It's difficult to find anything else in our experience that lasts this long unchanged. Mountains erode, continents drift, oceans rise and fall, species emerge and vanish. Even the stars themselves are slowly burning through their fuel, changing over time, though on scales even longer than planetary orbits. But orbits, once established, simply continue. They are perhaps the most enduring structures in the universe that we can observe directly. Not eternal, nothing is truly eternal, but close enough that the difference stops mattering on any timescale we can relate to. The Earth you're sitting on has changed unrecognizably since the Moon first formed. The surface has been reshaped countless times, the atmosphere has changed composition, life has transformed everything. But the Moon's orbit? Essentially the same. Wider now than it was, yes, drifting slowly outward, but still an orbit, still a circle, still the same fundamental relationship between motion and gravity. This persistence isn't magical. It's just what happens when motion exists in the absence of friction. When nothing interferes, nothing changes. The pattern continues, not because it's being preserved, but because there's no force present to disrupt it. And so the Moon rises tonight, just as it rose 1 billion years ago, just as it will rise 1 billion years from now, assuming Earth and Moon still exist in something like their current form. The same motion, the same path, the same gentle circling through the darkness. It's been happening longer than we can truly comprehend, and it will continue longer than we'll be here to see. There's something worth noticing in all of this. Something that goes beyond just understanding why the Moon doesn't crash into Earth. The universe, it turns out, has structures that don't require maintenance, patterns that persist without attention, without adjustment, without anything actively preserving them. And that's somewhat unexpected if you think about it. Most of the patterns we encounter in daily life need upkeep. A garden returns to wildness if you stop tending it. A building deteriorates without maintenance. Relationships require effort. Organizations need management. Almost everything we create or participate in demands continuous input to keep it going. We're accustomed to thinking of order as something fragile, something that naturally decays toward disorder unless we work to prevent it. And in many contexts that's true. Things fall apart, complexity gives way to simplicity, structure dissolves, but orbits are different. They're ordered, structured, patterned, and yet they persist without any effort at all. The Moon doesn't need to maintain its orbit. Earth doesn't need to manage the relationship. It just exists, stable, continuing on its own. This tells us something about the nature of stability itself, that certain arrangements once established are genuinely self-sustaining, not because they're being held in place by some active force, but because the conditions that would disrupt them simply aren't present. The Moon's orbit is stable not because stability is being created, but because instability has no mechanism to develop. There's nothing there to introduce change. And in the absence of disruption, the pattern simply repeats. You could think of it as a kind of equilibrium, though that word might suggest more balance and adjustment than actually occurs. It's more like a groove that's been worn so deep that there's no path out of it. Not because the walls are high, but because there's no force pushing toward the walls. This seems to be true throughout the solar system, throughout the galaxy, perhaps throughout the universe. Once objects find themselves in stable orbits, they tend to stay there. Not forever in the absolute sense. Catastrophic events can happen, collisions can occur, stellar evolution can disrupt everything, but for spans of time so long that stable becomes the most accurate description we have. It's a different kind of permanence than we usually encounter. Not permanence through resistance, through strength, through constant vigilance. Just permanence through the absence of change, through emptiness, through nothing being there to interfere, and perhaps there's something quietly reassuring in that. The universe contains spaces where things simply continue, where the frantic need for maintenance and adjustment and correction doesn't apply, where what was will continue to be, not through effort, but through the gentle persistence of motion in an empty place. The moon doesn't work to stay in orbit, it just does. And that simplicity, that effortless continuation, has persisted longer than almost anything else we can name. There's a certain quietness to this, isn't there? The idea that some things in the universe simply continue without drama, without crisis, without the constant possibility of failure. We live in a world where so much feels precarious, where things need tending, where attention lapses lead to problems, where the default state often seems to be decay or disorder. It's easy to internalize that feeling, to assume that everything requires vigilance, that permanence is always temporary, always conditional. And then there's the moon, just circling, not trying, not struggling, not at risk of forgetting how or losing its way, just moving through emptiness the way it has moved for longer than anything on Earth's surface has existed. It's not that the moon is special or protected. It's not that some cosmic force has decided this particular orbit matters and must be preserved. It's simpler than that, and maybe more profound. The moon continues because there's nothing there to stop it. And in that absence, motion becomes something like permanence. You don't have to think about it. You don't have to check on it. You can look up on any clear night and know the moon will be there, somewhere in its cycle, tracing the same path it traced last month and last year and 1,000 years ago. There's something calming in that reliability, not because it affects us directly. The moon would continue whether we noticed it or not, but because it exists as a kind of backdrop, a reminder that not everything is fragile, that some patterns are simply stable, genuinely stable, stable in a way that doesn't depend on luck or careful management. Other things in the night sky share this quality, the planets following their ancient paths, stars wheeling overhead in patterns that change only over millennia. These aren't things we need to worry about. They're not going to suddenly fail or collapse or drift away on any timeline that touches our lives. And maybe that's part of why humans have always looked up at the sky. Not just out of curiosity, though curiosity is certainly there, but also for that sense of constancy, that feeling of something larger and more enduring than the daily concerns and changes and uncertainties of life on Earth's surface. The orbits don't care about us. They don't exist for our benefit. They're not providing stability because we need it. They're just doing what they do, what they've always done, moving through space in patterns established billions of years ago. But we can notice it. We can let it mean something, even if that meaning is just the quiet knowledge that some things continue, that motion persists, that in the vast emptiness above us, the same paths are being traced tonight that will be traced tomorrow and next year, and for longer than we need to think about. It doesn't solve anything. It doesn't change the uncertainty of daily life, but perhaps it offers something nonetheless. A kind of background permanence, a reminder that the universe contains stability we don't have to create or maintain. Just the moon circling, just the motion continuing. So we come back to where we started in a way, to the simple observation that the moon is up there circling and has been for longer than we can truly hold in our minds. We've walked through the reasons why, the emptiness that removes friction, the motion that doesn't need maintaining, the balance between falling and moving sideways that creates a path which simply continues, the timescales so long that change becomes invisible, the stability that requires nothing but the absence of interference. None of it is magic. None of it requires special laws or exceptions. It's just what happens when objects move through space, when gravity pulls and motion persists and nothing gets in the way. The moon doesn't spiral inward because there's nothing there to steal its energy. It doesn't crash because it's falling sideways fast enough that Earth's surface curves away beneath it, and it will keep doing this, unchanged in any way that matters to us, for as long as we're here to wonder about it. Tonight, when you finish listening to this, if you step outside and the sky is clear, you might see the moon somewhere in its cycle, rising or high overhead or setting in the west, moving through the darkness the way it always has. And you can know now, if you didn't before, that this will continue, not because anything is projecting it, not because the universe has decided this matters, just because motion in emptiness simply persists. There's no urgency to any of this, no deadline, no crisis, no reason to worry that something might change. The patterns are old and stable and will remain so. You can rest knowing that some things in the universe don't need our attention, that the moon will still be there tomorrow and next month and next year, circling quietly, falling sideways through nothing, tracing the same ancient path. We've spent this time together exploring one question, letting it unfold slowly, seeing where it led, and perhaps now the answer feels less like information and more like something quieter, a reminder of persistence, of stability, of motion that simply continues. The moon doesn't need us to understand it, but maybe there's something peaceful in understanding it anyway. Thank you for staying with this, for moving through these ideas slowly, without rush. If you'd like to keep listening to more gentle explorations like this one, you're welcome to subscribe, but there's no pressure. You can simply let this settle and return whenever you'd like. The moon will still be circling, and we'll still be here thinking about the quiet mysteries of the universe together.